Hey folks, welcome to this episode on Introduction to Rates of Reaction. So, when we were looking at thermodynamics and thermochemistry, we saw that those equations and the graphical representations provided us with the information in terms of enthalpy change, but it never really talked about how fast that enthalpy change will take place. We could have a fast reaction with a huge enthalpy change, for example, like an explosion, or we can have some that are very, very slow in their progress. So the study of those kinetics, or the rate of change or the rate of progression, is called chemical kinetics, and it's the study of these reaction rates and also the mechanisms, which are events at the molecular level that control the speed and the outcome of this reaction. So what we're going to be looking at from this point forward in this unit is looking at how we can calculate rate and what kind of events help influence said rate. So what is a rate of reaction? It's looking at the change in concentration of a product per unit time. Now that's the rate of formation. Now you can also take the rate of consumption of a reactant or the disappearance, and that would be the negative of that rate. So in the case of a rate of reaction in terms of a product, which is usually what we measure, we have this equation over here. So our concentration of our final minus our initial concentration over the final time minus the initial time. So we're looking at the change in concentration over the change in time. And again, that's usually done for product, the formation of product, but we can also have the negative, which means the consumption of reactant. So if we look at this graphic over here, we can see that as time goes by, here's our time 0, we can see that we all have all reactant, it's in purple, and then as the time goes by, the reactant starts colliding with one another and creating product. And you can see that as this time progresses, we have less and less and less and less reactant until we get to a point where we have all product. Now, this is the main assumption that we're doing here is that this reactant, will go to completion and form only product. As we've seen in the past, this is not always the case. Sometimes we have a reversible reaction where reactant turns into product and then product turns back into reactant. But in this case, we're making the assumption that this reaction is going to completion. And you can see this in this graphical data. So if we analyze this, we see that as we have our change in time, we also have a change in the concentration. In this case, we're looking at B, the production of B, so our value would be positive. The change in B over change in time. We could also relate it back to A, but that would be the negative of the rate over here. So the concentration of A over the change in time. Now what you can see here is something very interesting. The purple is once again the rate of reaction for the disappearance of A. And the green is the rate of reaction for the appearance of B. So remember that purple is our reactant, green is our product. What you can see here is something very, very interesting. Initially, we see this rate is very steep. So the consumption of A is very, very steep. And as the reaction progresses, it becomes flatter and flatter and flatter and flatter. The steepness of the slope decreases. Now the same thing happens for B. We initially have a very, very high slope, and then it starts to taper off and plateau. Why is this? Well, you have to remember what happens in terms of reaction. For a reaction to happen, we have to have our reactants colliding with one another. They physically have to hit one another and have enough energy to actually react. Now, when we look at this, we have a high concentration of reactant. As this reactant starts turning into product, the green dots over here, we have less and less and less reactants. Less reactants mean less of a chance for an effective collision, effective meaning that we're going to turn into a product. There's less of a chance for an effective collision, and therefore the rate of the reactants converting into products decreases with time. So initially we have a high rate of reaction here because we have a huge concentration of reactants. But as those reactants turn into products, which we can see that they kind of go opposite to one another, as these reactants turn into products, there's less and less reactants to collide with one another, and therefore the creation of reactant to product starts to taper off. So we can look at different rates of reaction. We can look at an average rate, or we can look at an instantaneous rate. The average rate of reaction is shown by the secant. Now the secant is drawn by 2 points over some kind of time, and so we look at that change of reactant over the change in time. In this case, we're looking at the consumption, and it's going to be negative. If we want to find the instantaneous rate, what we'd have to do is we'd have to draw a tangent to that line and find the slope of the tangent. Now, this, we can use our calculus to figure this out because we're going into an infinitesimal small amount of time. But we use this tangent to figure out the instantaneous rate. And we can find an instantaneous rate anywhere on this slope. We can find it in the middle here, we can find it somewhere at the end here, or we can find it at the beginning. And that beginning instantaneous rate is usually what we call the initial rate. And that initial rate is what we usually use to figure out the rate of the reaction. Now, why do we use this instantaneous rate rather than some kind of instantaneous rate over here? That's because this instantaneous rate is where we have the highest concentration of our reactants. And as we said before, when we have a high concentration reaction, that means that the rate is going to be a lot more fast because we have more chances, more probability of having an effective collision. Effective, again, meaning going from reactant to product. As we go down here, we can see that our rate, the black line over here, starts to decrease because our concentrations go down. So typically, we use our initial rate because that's the point where we have the highest concentration of reactants, and that also is the time where the reaction rate for this reaction is the fastest. So when we look at our rate, we can calculate the rate of change of all the other species involved in the reaction by looking at the stoichiometry or the mole ratios between the species in this balanced equation. So here what we see is that the rate of production of this one right over here, okay, and that's C4H9OH, that's going to be butanol. We see that the concentration of butanol over time is given to us by this rate. Now, one thing that you should notice is the units for rate. They're mole per liter per second. Now, sometimes, remember that mole per liter is also big M, so sometimes you might actually see it expressed as big M over S. So it's the change of concentration over the change of time. We can see that the production of butanol is 1.00 times 10 to the negative 4 mole per liter per second. So let's see, how can we figure out what the rate of butyl chloride, this one here, or chlorobutane, is in terms of this. Now we can see from the balanced equation that we have a 1 to 1 to 1 to 1 ratio. And so to figure out what the rate of consumption of butyl chloride is compared to the rate of production of butanol, all we do is we take the ratios. So what we'll do is we'll take the ratio of the rate that we know, which is going to be 1, and take it and divide it, use it as the denominator to the coefficient that we have of the one that we're looking for. So we have 1, we take this one, bring it over here, and divide it. So it's creating a ratio. So 1 divided by 1 is 1. Therefore, if we have this, we have C4H9Cl, one of that, plus 1 H2O gives us 1 C4H9OH plus HCl. What we're going to see is that because this is a 1-to-1 ratio, the rate of this, 1.00 times 10 to the negative 4 mole per second, that's HCl, will also be the rate of this, 1.00 times 10 to the negative 4 mole per second. So the rate of consumption of butyl chloride is going to be the same as the rate of production of butanol because the ratios are 1 to 1. Now, what happens if the ratios are not 1 to 1? So in this case, when we have our balanced equation, we have dinitrogen pentoxide breaking down or decomposing into nitrogen dioxide and oxygen, we can see that from the balanced equation that they are not 1-to-1 ratios. So if we are given this rate over here, the change of NO2 over time is 5.00 times 10 to the negative 6 mole per liter per second. How does that relate, or how does that work for N2O5 and for oxygen? Okay, so if we're looking for N2O5, I'm just going to rewrite this equation here. I have 2N2O5, and that equals 4. Now the rate that we're given is 5.00 times 10 to the negative 6 plus oxygen. So to find what my rate for N2O5 would be, all I would do is I take this coefficient that we have over here, the coefficient, the one that I have, I'm going to take 2 divided by 4. So 2 divided by 4, 2 over 4, I'm going to simplify that, that turns into a half. So for every mole that's going to be created here, we have half a mole consumed over here. So if the rate for every mole here produced is produced at a 5.00 times 10 to the 6, that means that the rate of consumption for this should be half as much. So we have half multiplied by the rate of production of NO2, which is 5.00 times 10 to the negative 6, and we get 2.5 times 10 to the negative 6. However, one thing that we're missing here is that, again, this is a reactant. This is being consumed. So our rate for N2O5 is going to be negative 2.5 times 10 to the 6. So let's do the same thing for oxygen. Oxygen is a product. It's being produced along with NO2. But when we see this here, for every mole that's going to be produced here, we don't have a mole produced here. We have 4 times as much as we have over here. So our ratio in front of the oxygen is 1. We'll take our coefficient over here, we'll divide it by 4, and what we get is we get a quarter. So for every mole of this produced, a quarter of a mole is produced for here. So if this is the rate for 1 mole, the rate for this will be a quarter times this rate over here. So we take 1 over 4 multiplied by 5.00 times 10 to the negative 6, and that's going to give us 1.25 times 10 to the negative 6. Again, mole per liter per second. Again, I'll just put that over here just for completion's sake. Mole per liter per second. Now, in this case, the operation here is positive, or the sign is going to be positive, because it is a product that's being produced. So it's becoming positive there. So try this one yourself. Here we have nitrogen and hydrogen gases that react to produce ammonia gas, as shown in the equation below. The question is asking, what is the rate of consumption of each of the reactants when the rate of production of ammonia is 4.0 times 10 to the negative 3 mole per liter per second? So attempt this by yourself. Do one step for nitrogen and one step for hydrogen, and once you're done, come back and we'll show you the answer. Okay, so if we know that the rate of production of NH3, so change of concentration for NH3 over delta time is going to be equal to 4.0 times 10 to the negative 3 mole per liter per second. That's equal, not negative. Mole per liter per second. How does that relate to the rate of consumption of N2 and H2? So let's look at N2. When we look at our balanced equation, our coefficient in front of N is 1, and here we have 2. So our ratio between N2 and NH3 is going to be 1 over 2. Okay, so the coefficient of N2 is 1. The coefficient of NH3 is 2, so we have 1 over 2. So in this case, it's going to be this multiplied by the rate of the production of ammonia, which is 4.0 times 10 to the negative 3 mole per liter per second. And what we get is we get 2.0 times 10 to the negative 3 mole per liter per second. Now, once again, this is a reactant, so we're going to have to multiply this by negative 1 because it's being consumed. And so our final answer is going to be negative 2.0 times 10 to the negative 3 molar per second, or mole per liter per second. So let's do the same thing for hydrogen. Hydrogen, in this case, when we see here, hydrogen has 3 moles for every 2 moles of ammonia. So we have 3 divided by 2 multiplied by the rate of production of ammonia, so 4.0 times 10 to the negative 3. And if we take 4.0 times 10 to the negative 3 times 3 and divide it by 2, what we get is 6.0 times 10 to the negative 3 mole per liter per second. Now, because this is a reactant, it's being consumed, so let's multiply by negative 1, and we get negative 6.0 times 10 to the negative 3 mole per liter per second. Okay, so in this case, these are the relationships between our reactants and our products. The rates of a reaction are related, and they're related by the coefficients of the balanced equation. So thanks very much for watching. We'll see you next time.